This recording is started. So, student, welcome all to this lecture of CHI 130. We are discussing the chemistry of main group elements. In the previous lecture, we have learned about the hydrides of compounds of hydrogen, types of hydrides. Binary compounds of hydrogen is called as hydrides, and there are three main categories of hydrides we have seen, right? Molecular hydrides, saline hydrides, and metallic hydrides. And molecular hydrides further classified as electron rich, electron precise, and electron deficient hydrides. And we have seen the many examples. One of them is very famous, that is the diborane. B2H6, it is a dimer of borane. Borane is a BH3. Borane is BH3. Diborane is a dimer. Why dimer, diborane or dimer borane exists? Because BH3 is the very unstable compound. BH3 is called as a borane. CH4, like a CH4, there are 4 hydrogen with a carbon, CH4, methane. Similarly, boron having the 3 electrons in the last shell, and therefore it can form only 3 bonds. Therefore, it is called as BH3 borane, methane, borane, like that. So BH3, because of it is a electron deficient compound, BH3 is the electron deficient compound, and we know all electron deficient compound, they are called as Lewis acid. We know this well. And Lewis acid means they are electron acceptor. Any compound which is having incomplete octet act as an electrophile or electron deficient or Lewis acid. All terms are same for a one species. So BH3 is one of the very good example of Lewis acid, electron deficient compound, or we can say electrophile. Therefore, two BH3, they approaches each other and there is a formation of dimer called as diborane. We can say simply that B2H6 is a dimer of BH3. That's all. Now, there are many uh, theories explaining about the structure of diborane, and it is very simple structure but very interesting. You will find questions based on diborane also. So see, if you think about the valence bond theory, VBT, which says that each bond is consist of 2 electrons. Every bond is consist of 2 electrons. So if you think about this B2H6, if you think about this B2H6, so definitely these 6 hydrogen, these 6 hydrogen would be connected to boron. Yes or no? Yes. These 6 hydrogen would definitely would be connected to this boron. Yes, by 6 bonds. Each one hydrogen form one sigma bond. Hydrogen can form only one bond, and one bond means how many electrons? 2 electrons. So you think about it, when 6 hydrogen are combining with 2 boron elements, means there will be 6 bonds between hydrogen and boron. So 6 hydrogens forming 6 bonds. There are total 12 electrons. And similarly, there will be bond between boron and boron, because dimer only possible when there is a expected bond between boron and boron. This is what the expected theoretical idea we can say. So according to the VBT and Lewis structure, the expected number of electrons should be 14. Yes, 14 in the valence electron. Yes, it is expected to bind the 8 atoms together. So it is a very general concentration, general idea, general aspects approach, okay, according to valence bond theory. But this molecule have only 12 electrons. This molecule, this molecule have only 12 valence electron in a very specific way we want to say. 12 electrons. How? From two borons, it contribute 6 electrons and 6 from this hydrogen. Means instead of 14, it has only 12 electrons. So expected structure will not be possible. Understand the idea. The expected structure of B2S6 would be, according to VBT, that must contain 14 electrons. For example, you think about CH4. So how many electrons we are expecting? We can say, sir, 4 hydrogen means 4 hydrogen will form 4 bond. Fine, yes. So there are 8 electrons, and that's all. It's correct, right? Similarly, when you think about C2S6, C2H8, suppose, right? No, not C2H8. It is suppose C2S6. So logically, how what we think? See, like a B2S6, you think about C2S6. So C2S6, if you count the electrons, so definitely this 6 hydrogen will form 6 bonds, 2, 3, 4, 5, 6. And 2 carbons should be connected with another carbon. So only then there is a formation of 1 bond. So there should be 14 electrons and it is there. You think it is there. So therefore, this fulfill the VBT theory and rules and postulates. Fulfill. But in the case of B2S6, expected electrons are not there. There are 2 electrons. Means, therefore, the structure of B2S6 is somewhat different from expected. Okay? And it is because, so one sentence can be used to explain the bond. So the simple explanation is what? Its structure is the presence of BHB3 center. 2 electron bonds. This is the very basic foundation of boranes, in fact. BHB bond, that is called as 2 electrons bond. 3 center, 2 electrons bond. 3C, 2E. 3 center, 2 electrons bond. And these bonds, S bonds means plural form, more than one. There should be more than one. And definitely there is more than one. These bonds act as bridges between the boron atom, two boron atom. Okay, so it is a very basic idea, very principal idea of this structure of boron. There are two bridging BHB bonds. There are two bridging, okay, BHB bonds, and these two bonds are larger, longer in the compared to the normal covalent bond, and they are weaker also. While there are some other bonds that is called as a BH terminal bonds. So there are two types of bond in diborane: terminal bonds and bridge bonds. BH terminal bond, BH bridging bonds or bridge bonds. Okay, so you can think about one BH3 molecule which acts as a Lewis acid because it is electron deficient, and this BH3 will share its one electron. See, we can think about it also. See, see here, we can draw here, no problem. See, if you think like this, you see here, okay, yes, okay, fine. You see, here I am writing hydrogen, hydrogen, and hydrogen. Okay, right. So this B. So this BH bond means how many electrons? Yes, there are two electrons. Sorry. So we can write like this. We can write like this. See, like this. We can write like this. Fine. Whenever one more boron molecule approach to this, when one more boron molecule, we can say boron molecule approach to this, so what will happen here? See, very interesting point, very interesting point. So remember, always remember, in this, see, there is a one lobe. I will draw here. Okay, 1 minute. Yes. So see, understand this. It is like this, empty. It is empty. Okay, we will draw empty, no problem. This is empty, suppose. Fine. Okay, 1 minute. You see, this is empty p orbital on boron. If you think there is a one empty p orbital on boron, if you think about it. Oh, sorry. Like this, it should be small, slightly, like this. Okay. Similarly, so what will happen here? See, one will be here and another will be on this boron, fine, and another will be on this boron. Yes, see, I understand this point. Yes, fine, you are getting the point. Yes. So what will happen? This lone pair, which is in between this boron and this hydrogen, and you see, to understand this, I can also enlarge this, no problem. Fine. Yes. Okay. So you see here, there is a boron. Fine. You see here, there is a boron, right? See. So see these two electrons which are between the two centers, boron and, yes, boron and hydrogen. Therefore, this bond is called as two center two electrons. You are getting this voice or no? All of you getting this? This boron BH bond is composed of two electrons, as in the BH3 molecule here also. But this is a strong Lewis acid. So what will happen? See, this electron, these electron will be will be overlapping with this orbital. So what will happen? This will approach more near to this one. Fine. See what is happening? You tell me. You think about this. ये जो this hydrogen or this bond is overlapping with this empty orbital, and this bond overlapping with this empty orbital. We can say this one, right? See now, and that's all. You see here overlapping over. So this bond which was two center two electron, it was two center two electron, right? Yes, it was two center two electron. Now what happened to this bond? This bond is extended to this, up to this, like this, extended like this to this boron, and therefore this bond or two electrons, they are between this boron, hydrogen and boron. Similarly, if you see this bond is between this boron, hydrogen and boron, and this way these two bonds only out of these total six bonds, BH 6 bonds, two bonds become three center two electron. And definitely these bonds are a strong weak bond. Why? Because they have to delocalize. These two electrons have to delocalize between the three centers from this side, this side. Long distance is there, and we know if bond is longer, it is weaker. If bond is longer, it is weaker. Fine. So these bonds are called as bridge bonds, BHB bonds, BHB bonds, and these bonds are called as terminal bonds, BH bonds. So this is what about the explanation of the uh, diborane structure. Just we have seen. Okay. So see, you see here, one BH3 moiety is a strong Lewis acid and gains the share of an electron pair from a BH bond. Just now we have seen. In other BH3 moiety, hence involved in dimer formation. So hope you understand this idea. Right? This is what about the structure for diborane, which is just now we have discussed. Similarly, you see, similarly, other compounds, alumina, this is alane, ALH3 is again is a very good example of uh, uh, again Lewis acid. Okay, but it is also uh, neither exist as a monomer. This ALH3 is one of another member of this boron family that also do not exist as a monomer or dimer. However, it forms complete continue compound called a polymer. Okay, what is polymer? It's continuous long macromolecule. Okay, yes, and beryllium is also one of the compound which form the hydride, beryllium hydride, which is the example of again electron deficient compound. So this form the polymeric BH2 means B2 BH2 involved in polymerization instead of dimer trimer it form very long chain continuous chain, right? Yes. So BH3 do not exist as a monomer, it exists as a dimer. ALH3 it exists as a polymer, and other compound also they exist. In addition to these, about boron hydrides, okay, these boron hydrides or boranes, they also interacts with the sodium hydride and they form sodium borohydride, NaBH4, and lithium aluminum hydride. You remember the formula, lithium aluminum hydride. These are the examples of hydrides which are exist in the form of a hydride salts, we can say, and they are of very much great use in the organic synthesis. Fine. Okay, fine. See, another compound is what?